Okay, great. Is there actually a speaker in here? Or maybe this is for the camera. Okay. Right, so I'm going to be considering the simplest possible theory on this background, which is just a minimally coupled massive scalar. So I'll have an action that looks like this. And I want to organize this theory into SL2R. I can do it in the following way. I can think about the single particle states of this scalar field. And notice that those single particle states lie in irreps of SL2, or can be organized as irreps of SL2. And the reason for this is that SL2 emits a set of killing vectors, or sorry, this geometry emits a set of killing vectors that actually obey the SL2R algebra, which is so a trivial statement since we already know that this is the SL2R is the isometry of this. But there's a set of killing vectors I'll call zeta, which obey the SL2R algebra and whose Casimir also realizes the hyperbolic Laplacian acting on these scalar fields, right? So this tells us that the mass shell condition for the scalar field is nothing more than setting this Casimir equal to m squared, okay? So then we can now look for representations that satisfy this, and these will be some infinite dimensional highest and also lowest weight irreps, which with highest or lowest weight labeled by J. And their Casimir satisfies J, C equals J times J minus 1, which tells us that J can be 1/2, 1 plus m squared plus 1/4. And I'll often call this quantity here nu. Okay, so far we have 2 branches for this J. So right now I should be saying things that are pretty standard in the ADS-CFT dictionary. Now we'll want to impose some Dirichlet boundary conditions on phi, and that will normally come in the form of the normalized will fall off of its wave functions, and this will pick out a particular sign of J here, and without loss of generality, I'll pick the positive sign. So J will be 1 plus nu. Okay. So this will be the single particle states be labeled by these highest and lowest weight representations with J given the following form. Okay. So now I want to actually consider the one-loop determinant of this scalar field and try to realize it as a topological operator in this BF theory, as I was promising so many times yesterday.
J is the dimension of the boundary operator?
Yes, yeah, if you like. Yes, it is the dimension of the boundary operator. Okay, so the one-loop partition function, which we'll call Zm, is nothing but the functional determinant of this Casimir, or this Laplacian minus m squared. And I had claimed previously that this could be realized as a topological operator. I'm going to rewrite that claim here, but in a more precise version. For JT theory, for JT gravity. It's going to be some polynomial in nu, which will need to be set by a renormalization condition, and then something that is non-polynomial, which is this guy here. And what we'll see is that there'll be a renormalization condition where I can state this completely in representation theoretic terms as negative C2 minus a quarter. And then this W is this so-called Wilson spool. This will be the lowest weight representation of J, although I have in my notes highest weight. Okay, I'm going to assume that I meant lowest weight, but no, I'm going to trust what I had written before. Okay.
Lowest or highest depends on, I don't know, this is SL2R representation theory, right?
Yes, so.
Whether you are killed by the analog of.
Yes, it depends on, so it's going to change actually which contour I need to pick here so that this can actually converge. So this will be a detail that I will now say if you really, really want to be kosher on this, look at my paper to make sure that the contour matches whatever representation I choose here. I'm going to write what's in my notes and then hope that I was sane when I did that. Ultimately, whatever representation here is tied to which contour you pick here, and you can there's some choice that you can make. Where this gamma runs around the point in this disk, but in more general cases, should run around 80 non-contractible cycles. So I'll give some further use cases for this at the end. A was the connection of the BF theory.
That is dual to this particular job.
Yes. Yeah. Okay.
What's the radius of this?
What did you say?
What's the radius of this?
It can be any radius because it will only depend on the holonomy of A. Yeah. Okay. And then this contour in alpha is the following contour. I pick just to the left and right of epsilon, or some distance epsilon, just to the left and right of 0. So right now I'm going to just draw the poles from this this measure. And it looks like from here that the only thing that this contour does is just avoid the pole at 0. However, there will be more interesting geometries we can think about which might have more interesting pole structures along the imaginary axis. So here it's for the disk, it looks a bit trivial, but I've chosen this specifically. So there's C alpha. It's not a closed contour; it's an open contour, and this has to do with it being in 2 dimensions as opposed to higher. But we'll see that also the fact that it's an open contour is going to be necessary for reproducing certain logarithmic divergences that appear in 2D that don't appear in other dimensions.
So in the alpha plane, you have 2 things going on?
Yes.
Are separated by that singularity and alpha equal to 0.
Yes. Yeah.
And then, I'm really sorry not to belabor this point, but I now understand that you're, in JT theory at least, because your matter doesn't couple to the dilaton,
Yes.
you know, the dilaton path integral, if you do it the standard way, will set R equal to 2.
Yes.
In the quantum theory.
Yes.
Then, given the topology that you're using, you can really set the metric once and for all
Yes.
to be one God-given metric with which you started. That gives rise to this gauge potential
Yes.
A, and then it only depends on that.
Yes. Yeah.
That's because it's a very special theory where the metric
Yes.
sense for this topology just does not fluctuate.
Right. That's right. That's
In a
right.
rigorous
Um,
integral sense.
I'll also comment at the end as well where back reaction from the matter does arise, which is on the boundary, which we are so far ignoring all the boundary wiggles. We're computing.
On the boundary, of course, matter will couple to the Schwarzschian,
Yes.
et cetera, et cetera. But here, just for the bulk, right?
Yes. Yeah. I'm calculating bulk one-loop determinants here.
What kind of trajectories does matter emit in this geometry? What is the
kind of-
solution to the equation of motion for particles like matter with the dilaton? Well, it's not coupling to dilaton, I guess.
It's not coupling to-
geodesics has to be geodesics, right? If it's
Yeah,
very
yeah,
massless,
yes.
I mean, very light, then it will be geodesics.
Yes.
But then there is no geodesics like that.
So there.
It's
So,
very massive, actually.
actually,
Without back reaction, that's
It-
what I meant.
it doesn't couple to the dilaton in the in the action, but if I vary with respect to the metric, it couples to the dilettante equation of motion, which is I can't. It's at the end, but it's something like.
I mean, the equations are mixed, so the variation of the dilettante will set R equal to 2.
Yeah.
But this, of course, couples to the metric. So
Yeah. So in some sense, its equation of motion is coupled to the dilettante, but it's not coupled to the dilettante in the action. This is why I said the back reaction happens at the boundary because this changes the dilettante fall
There
off.
are these trajectories also which are just going around in the disk, which are equations of motion for matter.
I honestly have not studied it, so I can't say for sure. But I think if the matter is following geodesics, then there would be, well, let's see.
Then clearly not, right? That's not.
Yeah, it would.
zero extension.
Yeah, that's right. It would be.
So I should not think of this curve as some sort of a line that matter is following.
No.
Because we also talked a little bit about this two-loop exactness, where the starting point was the saddle point, where
Yes.
you sign the equation of motion is geodesic,
Yes.
and then you function. That's not the point of view now.
No, I mean here it's just I'm looking for any cycle that has non-trivial holonomy, right?
Sorry, where does this formula come from, roughly?
I'm going to explain that just now. Yeah. First, I'm going to show you that it gives the right answer on shell. So I'm going to test this first, and then I'm going to derive it, if that's a sensible order for things.
just to make sure, this is all Euclidean ADS.
Yes.
Right?
Yeah. Okay. So first, I'm going to test this on shell. So I'm going to take the connection that I had here, or more specifically, I'm going to take its holonomy.
Sorry,
Yeah.
should I roughly think of this like as computing like a determinant in a black hole background? Because a disk
Yeah.
is like a,
Yes.
the Euclidean part of
Yes.
background.
Yes.
So, for instance, one way to compute this would be from this Denef Hartnell such.
Yeah. That's what I'm going to do.
Okay.
That's exactly what I'm going to do.
The structure is very similar. This polynomial of mu.
Yes, it's you're either you're totally reading my mind or you read my paper, but either way you read something, and this is exactly this is what we're going to do. Okay.
And just for my benefit, the
Yeah.
integrator over alpha, should I think of as like implementing the summing over?
So I'm presenting things a bit chronologically backwards. In 3 dimensions, yes, it really does. So in 3 dimensions, this is not an open contour; it's a closed contour, and the closed contour wraps poles and gives windings. Here, because it's open, it's a bit. It depends on the specific instance. So we call it a Wilson spool because we invented it in higher dimensions where it actually has this wrapping interpretation here. There are other geometries in 2 dimensions that at the end I'll mention that do have also this structure. But for this one, it's because it's an open contour, it's just whatever the contour gives. Yeah. Okay. So the on-shell test. So I take A. I recall that A has a holonomy around this, which was, if I can write, e to the I2 pi p0. Was that the correct thing? Yep. Okay. And so I can compute the character of this. So now this trace here just computes a character of a highest weight representation. And I can compute what this guy is. And so now I see that, okay, this guy has indeed its own poles, but these poles actually match up with the poles here. So they just add on, they just double the poles that arise there. Okay. So now I just have to do this integral. Now this is some function of alpha, and there are various tricks for doing this integral. And I will not bore with details of that, but it is in an appendix. And these are now Hurwitz zeta functions.
Sorry, highest weight is or lowest weight is mu? I'm
Yeah,
trying to
yeah, yeah, yeah.
understand that shift by half.
Yeah.
So I would have expected weight of the highest weight,
Yes.
and then 1 plus e to the power I alpha for the derivatives. Why is
Yes.
there an extra, sine has an extra e to the power I?
It's like just 2j minus 1, right? So you start with, it's either I, so you have a j here. Why is it not an alpha over 2? Maybe it's an alpha over 2. I have an alpha there, but
It's a very important question. Sorry, I would have expected that the states be highest weight, then highest weight plus 1, highest weight plus 2, and so on. Those
yes.
or lowest weight plus 1.
Sorry,
So-
it's highest weight minus. Yeah.
Highest weight minus. So the numerator is giving that highest weight.
Yeah.
And then this, the sign is like you take something out and then there's
Yeah, yeah.
1 minus.
Yes.
But why? But there's an extra half.
Yeah. So it's a yeah, good. It's like a 1 minus e to the negative alpha, or I alpha, and then I multiply, and this would have been a I alpha j.
So
And-
the j is nu plus half.
Yeah, and then I multiply e to the negative 1/2.
Sorry, but the j was nu plus half then.
Yeah.
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 See,
It's
what
right
is
here.
that J is
Nu plus half. Thank you. Got it.
I thought your question was why is the denominator
No,
also
that-
with a half?
That puts that half on instance. Yeah.
Okay.
Because the relative thing between the two is fine, good.
Okay. So now this indeed matches various previous computations by heat kernel of log zm up to this polynomial, which if we use the heat kernel as our whatever, so again, if we have this polynomial term, we have to set a renormalization condition to set it, and I'm going to set it as I want it to match the minimally subtracted heat kernel, and then this just determines PV to be negative C2 minus a quarter, which now I forget what C2 was. I don't know, J times J minus 1 minus a quarter. But, okay. Good.
It's like often when you have integrals of this form,
Yes.
the coefficient is like a van der Waals kind of thing. Is
Uh,
that the case here? Meaning this is like a character,
Yes.
and then you are doing the integral over the eigenvalues, and a natural integral is eigenvalues, van der Waals character.
That's a connection I had not made. I don't.
Just making the group measure.
Yeah.
Just turning it to the measure the group measure. Is that somehow the case? Probably not.
I don't know. This is a connection I had not made. Yeah. There. So I will mention that this also the structure, this idea that you have a contour integral, some sort of measure here that has poles in the plane times a character is something that has also appeared in various contexts in De Sitter and also ADS black hole physics by Zemo Soon and Albert Law. And so there seems to be some general structure to one of the determinants having this kind of form. Okay, and so now I'm going to get onto a derivation of this, and it will indeed use this quasi-normal mode method of Sachdev, Hartnell, and Denef.
Yesterday's talk you said you were going to use the saddle point, like you're going to first find the saddle point of the world.
That's going to be in 3 dimensions for ADS 3. Yeah.
You could you not have done that?
Well, here this guy is not geodesic, right? And it's because it really wants to shrink to 0. So I mentioned yesterday that there's a problem with cusps and conical defects. Here, these are cusps you can think of as like 0 length geodesics. In some sense, this guy wants to be like that. It wants to be something that shrinks to 0 size, but it can't because of this flux. So this is an example where I can compute such a thing, but I don't know how to do it in higher dimensions. If that makes sense.
I mean, it's strange, right? Like the metric doesn't have any cusp.
Yeah, that's right.
Very smooth.
Here, I'm going to derive this from a completely different method here. Yeah. Okay.
But I mean, probably what it is that you still have a non-trivial problem. I mean, even if you did it batch-wise and glued right within Fakta way,
Mhm.
probably
probably coming from random.
Yeah, this is,
Okay, I see. You're saying that even if it's zero length, it still has some
You have fluctuations around zero.
No, I was worried about the holonomy.
Well, suppose we were just doing it from the metric point.
Okay.
Yeah.
Then there's no holonomy anything, it's just a smooth metric. But there's a zero size guy. The guy probably wants to, I suppose.
I mean, there's no other, if I'm not talking about things anchored to the boundary, I'm just talking about closed geodesics here, then that's the only class of geodesic there. It's just that geodesic.
Now this is like a Euclidean kind of problem, so there's no natural point. Could be anywhere.
Yeah, exactly. That's right.
What?
There's limit how, right?
But the matter doesn't seem.
Matter
This is
is
coupled
zero.
only to the
And the connection is flat except for the origin.
Yes.
If I remember yesterday.
Yes.
Right?
If you think of it like this, but if I just think of it as a scalar field on a metric, then it's just a scalar field in areas 2, Euclidean areas 2, it's completely translation indirect, right? So why am I getting an infinity, a volume of areas 2?
There is apparently.
Oh.
Is that 1 by epsilon? Or maybe that's in the polynomial renormalization?
Oh, so that's the part that
No.
we renormalize away from the
Yeah,
boundary.
so I think in the heat kernel method, yeah, actually the heat kernel would also have this 1 over epsilon divergence, and you use a renormalized volume there. So the volume is strictly infinite,
Yeah.
but then you add the boundary counter term,
Okay.
and then you render that finite, and actually ends up being negative, and it matches this 1 over epsilon squared.
So this is probably tied to some boundary cosmological constant
Yeah, that's right.
contribution, right?
Yeah, yeah,
Probably.
Yeah, this is
And
the fact that
log maybe some higher.
lengths and volumes grow the same way, so you can get rid of it, right? And, okay.
Okay, so I'm gonna work with the quasi-normal mode method, and I'm going to basically use the method by Denevs, Hartnell, and Sachdev. But I'm going to tailor it to work with it in a representation theoretic manner. But
If you're not going to say this because there's so many experts say it anyway, as to what this method has always been explained to me many times. How is it mysteriously that you compute this determinant from quasi-normal modes?
so I'm going to explain. We're going to use the ethos of this method. Okay. And the ethos is the following. We're going to treat Zm as a meromorphic function of this parameter nu, and we're going to now continue nu into the complex nu plane.
Explain the ethos, but can I just ask you a question as
Yeah.
an aside, which is to compute determinants in de Sitter also, you can do it by summing over quasi-normal modes
Yes.
in de Sitter as well?
Yeah, so that's actually our first paper on this was written for DS3, and this is the breakthrough is when we realized that you could do this, and then this led to this. Yeah. This method ends up being a bit easier to explain in 2D, and hence I organized my talk. I'll start with 2D, and I'll start with this quasi-normal modes, but it's a bit chronologically backwards. We start in 3D with the sitter, which will be the very end, actually. Okay. And as a meromorphic function, then it's fixed up to overall holomorphic function, so e to the p of nu, times the rational product of its zeros and poles. And since this is a scalar theory, we're going to notice that, well, actually I should be working with z squared here, but z squared is an inverse determinant.
And why is it a meromorphic function?
This is a genuine assumption that we're going to make.
Oh,
Yeah, this is always the starting assumption of this this method. Yeah. So the z squared is going to have poles whenever on any states that satisfy the equation of motion here. And so this is so in Euclidean signature, these are just actual normal modes, but then I interpret these as continuations of quasi-normal modes in Lorentzian.
I mean, if I get my signs right, yeah, which is minus del squared plus m squared is a positive definite operator, right? So there should be no zero once m is non-zero, right?
That's right. But here we're so.
But now you think of it as an analytic
Yes, yeah, good, yeah. So,
Function for any new.
yeah. You need
So
you need
therefore-
you need to solve this for any new, in particular, yeah.
Now I got it.
Yeah.
Okay, sorry.
So the new was what?
Square root of b square root.
Yeah.
Yeah, mass.
New, so new was related to the highest weight J here, and then J was related to the mass in the following way. Okay. Presumably I also had an actual just relation between new and m.
Square root of b squared over 4 plus.
Yeah. So this new squared is m squared plus a quarter. Okay, and so we can think of log of Zm as the sum over the quasi-normal mode spectra, which will then lead to its expression as a spectral zeta function. So what we're going to do is we're just going to take the same ethos and we're going to adapt it to SL2, our representation theory.
Sum over quasi-normal spectrum is.
Yes, it leads to a spectral zeta function.
Which is the determinant.
Yeah. Yeah, so,
Zeta to the eigenvalue.
yeah. Okay, so so the first thing I wanted to remark on is that this z squared, again, I'm going to now think about it as a determinant over a Casimir, an SL2R Casimir here. I'm going to impose several conditions on finding where the poles are of this function as a function of nu. So this is a Casimir that's a function of nu, So the condition 0 is that the poles will line up whenever there's a state such that this, whatever's in this determinant is 0. So poles of Zm squared align with weights of representations satisfying the mass shell condition. So that's C2 is equal to m squared, which we saw led to these highest and lowest weights with J1 plus nu. So then there's a condition 1, which states that I'm not going to do, so my integration over field space is not over all fields, it's over fields satisfying some boundary conditions, right? So this will be the non-trivial condition here. I need to impose boundary conditions. So one condition is a weight can contribute a pole. If it corresponds to normalizable. Corresponds to a normalizable fall off, and what we normally don't even think about but should still be true and is single valued everywhere. So this first condition, as we stated, picks out a particular J. So set J is 1 plus nu. And the single value condition is now the non-trivial thing, which says that under any closed cycle, if I parallel transport this with my connection, a weight can contribute a pole.
Oh, can.
Yeah, if it corresponds to normalizable fall off and is single valued. So this field living in this representation J, if I parallel transport it with my connection here around any closed cycle, should return to itself. So then this gives us a condition actually on the weights of the representation in terms of the holonomies of the. So this tells us if lambda is a weight of Rj, and h is the holonomy of A around this cycle, then lambda times h needs to lie in the integers here.
Yeah, this is an assumption, or you're,
Well, no, this is just so.
this follows from your.
This is just imposing just that this field is single valued as a parallel transport around any cycle.
What was it imposing? Suppose I just thought of it as a field theory on a metric.
Yeah.
Is it imposing some constraint on masses?
It would be, for instance, I think we normally build this directly into the types of wave functions that we try to solve this equation for, this equation. But since I'm building these out of representations, I'm now thinking about them as under their action of parallel transport of A.
But I thought if I just had a scalar field theory with some
Yes.
mass, that gives me one of these modules.
Yes, that's right.
So this module is a highest weight or lowest weight or whatever module. And given a mass, I know my highest weight. So I thought
Yeah.
I got everything out of that as I vary over the space of all masses.
Mm-hmm.
I don't see where from that becomes any further constraint.
Can I just, sorry, but
Yeah.
please answer Shiraz, but just put one question on the table. Just
Yes.
Quasi-normal modes are in the Lorentzian case, right?
Yes. So
But
these.
at least there, I would just take this field of given mass and I would solve for the modes subject to boundary condition, and whatever I get, right?
Mhm.
And presumably summing over those give you the determinant, right?
Yes.
And now these conditions are, if you're casting that question in first order formalism.
Yes, that's I mean, in essence, we're casting this in first order formalism, and we're also trying to really keep it as statements about representation weights.
Sorry, just to understand, I thought that there was a
Mhm.
one-to-one map between masses and representations. And so
Yes.
and since I felt like we could work with any mass, that's probably my problem. I didn't see where you're getting constraint on it.
When you change your weights, you're changing the masses or you're changing the number of derivatives?
Sorry. It's so no.
Highest
You.
weight is the mass, and then the derivative structure is just that constraint.
So one way you can think about this is that.
So this is a constraint on the mass. This
No.
constraint that,
This is a constraint on the weights of the representation, which then tells you, for instance, what is the order of a pole at a given mass. So I'm varying this in the mass plane, and then all of a sudden I hit a value of the mass where now Z has a pole, and I hit it, and the order of that pole is the number of representations that satisfy this condition, or the number of representation weights. Yeah.
Number of states in that representation.
Yes.
In Euclidean, in terms of Euclidean solutions, you also want to impose some regularity conditions near the backward horizon.
Yes. Yeah. And so this is very much yes. This is the same condition there.
Wait, but every state in the representation is regular.
No, but if you vary m square, take m square to be some complex number.
Yeah, so this is also the non-trivial thing in the DHS method as well, is that imposing that these guys are regular at the black hole horizon is.
Wait, this character is not an analytic continuation from real masses. Say,
Yes. This.
If I took Euclidean mass to be real, I get a character formula.
Mhm.
Then this character here is not just analytically continuing that.
It is analytically containing that.
So then that whole character formula, every state that contributed there was regular.
Mhm.
So
No. Sorry. No. This is a non-trivial constraint on the weights.
I understand it's not trivial. I just
And we have also, for instance, verified that the number of poles that you get from this recasting is also the same number of poles that you get from the normal
I'm sure
DHS.
it's correct. It's just probably my ignorance. Let me understand. Is this a constraint on the mass or constraint on which level number?
It's a constraint on the weights. It's a constraint on so what it tells you is what's the order of the pole of a mass that now satisfies the quasi-normal mode condition.
I think the states in the representation.
Yes.
Right? How many states in the representation obey this, and that is
Yes.
the order of the pole.
Yes, exactly. So again, it's very much like Onkar said. That it's the corresponding thing that this condition is in the original paper by Nev, Hartnell, and Sachdev is infalling boundary conditions on the black hole.
So are you saying roughly that half of the modes will obey this?
Not for all values of masses, I think, because these will appear at certain poles will be
Yes.
with mass planes some places, right?
Yes, I can't answer that question definitely, but I don't think it's just like as simple as roughly half the masses.
So just to say, what I can understand is this, that if you do an ingoing boundary condition,
Yes.
then analytically continue that to Euclidean space,
Mhm.
that will be either a decay or a fall off depending on detail.
Yeah.
And if you want, perhaps you're saying only the modes that fall off contribute. from
That's
the
I think that's roughly.
quasi-normal
I
mode.
think that's roughly what I want to say. Yes.
Okay, but I would have said the same thing, you know, if you translate in.
Sorry, actually, no. Yeah, sorry. The difference between infalling and outgoing actually is the difference between lowest weight and highest weight here.
Okay, good.
But here this is more about and regularity at the horizon.
Yeah, I was
Yeah,
going to
yeah,
say,
yeah.
I think at the bifurcate, you know, the condition, because you don't distinguish between in and out in.
Yes.
Euclidean.
Yeah.
So the only condition is regularity.
That's right. It's regularity, but the towers split up into this. So there's. I was careful to keep both highest and lowest weight, and the highest weight and lowest weights actually correspond to the ingoing and outgoing.
Good, so these are
and towers.
quasi-normal modes and anti-quasi-normal modes,
Yes.
that I understand.
Yes.
But I still don't, maybe you can go on, but I still don't understand. In Euclidean space, suppose we were just in Euclidean space and masses
Yes.
were real, then every mode in the thing is regular, right?
Yes, that's right. So
So now what is changing as you move?
so I mean.
What do you mean? You're getting zero modes for quasi-normal modes?
Yeah.
No, but maybe I'm just not understanding. I thought you were saying that there's a character that you're analytically
Yes.
continuing and something changes about the character, that you're only allowed to keep some modes in the character?
Sorry, I'm continuing an entire representation all the way to that representation. I'm only keeping weights in that representation that obey this
What does
condition.
it mean that you only keep it?
So, or what I'm saying is that I'm keeping track of the ones that obey this condition, and that tells me an order of a pole at that value of mass. Yeah. So in some sense, all this is doing is it's counting how many weights, and then that tells me an order of the pole.
But in Poorman's language, in the second order formalism, would you say that for some arbitrary complex mass, even imposing regularity at the origin, and I'm not quite sure what you're doing at fall off at infinity,
Yes.
you get a non-trivial zero modes of the Laplace.
Yes.
That's what.
Yes. Okay. So good. I'm going to take this, these conditions, and from this, I'm going to construct a meromorphic function that should give me. I probably did not want to erase that because we're always going to get confused about how nu is related to the mass. So I'll write it as up here. Nu squared is m squared plus a quarter.
Sorry, so one last question about this. Such that then if an afternoon or maybe then if later on, and something special happening to higher spin fields.
Yeah, we're also going to get to that, but that will be tomorrow.
But this is not that.
This is not that. So first off, so the spins are not going to play a game in 2 dimensions. They'll play a game in three dimensions. In ADS, the spins just go through fine. In de Sitter, though, we do have to be very careful, and it does come underneath this condition that you have to be very careful on how you deal with the spins. So yeah, we'll worry about spins. Okay. So I can write z squared as the following. So I have, again, some polynomial in nu that I have to fix. So I have a tower of poles for both the lowest weight and the highest weight representations. And then I also have this product over n that then implement that is basically the product over the weights that obey this quantization. And H, I will remind you, is the holonomy of the gauge field around